electron configurations of ions. So anions gain electrons. That means we're adding electrons to their electron configuration. We need to be able to write an electron configuration for an ion. Cations are formed by losing electrons. So then we have to subtract electrons from the electron configuration, and they will be subtracted from the valence shell. So let's look at an example here. So aluminum, here is its electron configuration. 1s2, 2s2, 2p6, 3s2, 3p1. So we know it becomes a plus 3 ion. We need to remove 3 electrons. We're going to take the valence electrons off. So the valence electrons are these 2 and 3s, and those 2. We get rid of those, and now we have 1s2, 2s2, 2p6. And this is the same electron configuration as neon. Any questions? The adding, you just keep going. That's not as tricky. So, of course, the transition metals have to be a little bit troublesome. Here, it's important to remember, and I will try to trick you with this on an exam, it's important to remember that you don't just go in reverse order of filling. You remove the valence electrons first. Okay? So for this iron atom, its electron configuration is shown here, and when we talk about order of filling, the 3d6 orbitals got electrons last, right? And so it's kind of natural to assume we'll last in, first out. The valence electrons get lost first. So, we've got 1, 2, 3, and 4. 4 is the largest big number in the valence in the electron configuration. These are the valence electrons. So we're going to take those out. So those are valence electrons. We get rid of those. That gives us an iron 2 cation. Okay? We need to lose another one. Well, now we can just go by reverse order of filling because these are all the new valence electrons. So we're going to take out one of the 3Ds. Paused it again by accident. An atom or an ion is paramagnetic if it has unpaired electrons. So it will be attracted to a magnetic field because those unpaired electrons will generate a magnetic field, and so they'll be attracted. When they're paired up, they're like too busy to get into magnetic fields. And then diamagnetic is the opposite, where all the electrons are paired. These atoms and ions will actually be slightly repelled by a magnetic field. So how do you keep these straight? Because di means 2, but para sounds like pair, right? P-A-I-R meaning 2. What do I do? So di is definitely 2, right? Di is 2. So here in diamagnetic, they're going 2 by 2, like Noah's Ark. The animals went in 2 by 2. Diamagnetic. They're going in 2 by 2. Everybody's got a partner, right? There's 2 giraffes and 2 elephants, etc. So this is the opposite way where they are not paired up. Okay, that's the best I can do. Noah's Ark. Okay, write electron configurations and predict whether each is paramagnetic or diamagnetic. They want the electron configuration and the orbital diagram. So we're just going to use the noble gas configuration. So cobalt, the previous noble gas is argon. You know why there's no good chemistry jokes, right? All the good ones are gone. Sorry. After argon, we get to 4, 4s2, And then the next part is 3D, because that sank down, right? And we count across 1, 2, 3, 4, 5, 6, 7. So that is for cobalt, the atom. And then let's do the orbital diagram as well, since they want us to do that. So this is 4s, and this is 3d. So there's 2 electrons in 4s. There's 1, 2, 3, 4, 5, 6, 7 in 3d. So cobalt 2 plus. How many electrons do we lose? 2, right? Which ones do we take off? From the 3d or from the 4s? We're going to take the 4s electrons off because these are the valence electrons. So those are the ones we're getting rid of. And so the electron configuration for the ion is going to be argon 3d7. Occasionally you might see 4s0, but I don't think that's required at all. So if we're looking at the orbital diagram, which electrons are we going to erase? The 4s ones, right? Get rid of those guys. So that's the cobalt 2 ion. So nitrogen. Well, nitrogen based on helium, not much of a shortcut, but whatever, right? And then 2s2 and 2p what? For the atom. And if we look at orbital diagram, we've got 4s2 and 3d. I'm sorry, I don't know what I'm saying. 2s2 and 2p3. Just listen to what I meant to say. So that's the atoms. Those are the atoms, right? And 3 minus, what do we need to do? Add electrons or subtract? Add. How many? 3, right? So if we're going to add 3 electrons over here, we're going to add them into this last level, right? So we're going to add into here. So we're going to end up with helium 2s2. 2p6, which is the same as neon, right? And over here, if we're going to add 2 electrons, where do they go? They also go in the 2p, so this one pairs up and that one pairs up. So those are the configurations for the ions. Okay? So you start with the atom, and then you take away or add electrons to get the correct charge. Now we have to do this part. Are they paramagnetic or diamagnetic? Which is which?
Para is where they don't have and di is where they have 2
2 is where they're partnered up. Yep, everything's paired up. 2 by 2, Noah's Ark. So, are all of these electrons paired up? No. So this is not like Noah's Ark 2 by 2. So that must be paramagnetic. Question?
Why is there 5 electrons in the
Oh, that's an excellent question. Thank you. I'm glad you asked that before we got there, because I was wondering why they were both the same answer. Yeah, because I was testing you. Yeah. No, because I'm half brain dead. Okay, so this one is paramagnetic. that will be slightly attracted to a magnetic field. You can think of these guys as like looking for somebody to spin with, right? And down here, like Noah's Ark, 2 by 2 by 2, all paired up. Diamagnetic. Any questions? We can also look at trends in ionic radiuses, radii. So let's just think about this. A cation is made by taking electrons away. You would expect that to make the atom bigger or smaller? Peel something off the outside. Should get smaller. It does. It actually gets a heck of a lot smaller, because you've lost the entire valence shell. And so you're going down a level. And so what we see is that cations are roughly half the size of the atom. So removing a couple of electrons, removing the valence shell, makes them much smaller. It's not only that we've removed an entire layer on the outside, but that changes the calculation of the effective nuclear charge, because now what were core electrons are now valence electrons, and so you're subtracting fewer core electrons and the effective nuclear charge is much higher. And so those two things combine to just really shrink it in, okay? If you need to compare like lithium ion and rubidium ion, well, it's going to be the same as lithium and rubidium compared to each other. We're going down a group. They get bigger as they go down. Rubidium ion is bigger than lithium ion. What about anions? Well, anions are larger. Yay, something that makes sense. Right? So you've got something and you put stuff on the outside, you expect it to make it bigger. These get bigger. And here what's happened is we're adding electrons and there's no change in the nucleus. And so the effective nuclear charge becomes lower, and that loosens things up. So there is also a large change in radius, but not quite as big. So anions are bigger because you added stuff to them. Cations are smaller because you took stuff away. Bless you. Then we have what are called isoelectronic ions. So that prefix iso means same. So the same electrons. So these are ions of different elements that have the same number of electrons. They have different protons, but they have the same number of electrons. So most of those main group elements, when they form ions, they have the same electron configuration as a noble gas. So if we look at these guys, sulfur sulfide ion, S2 minus, Cl minus, K plus, and Ca2 plus. Okay, all of these, because there are ions, have 18 electrons. They have the electron configuration of argon. What's different is the number of protons. Sulfur has 16, chlorine has 17, potassium has 19, calcium has 20. So is 20 protons going to pull the electrons in tighter than 16 protons? Yeah. If you calculate the effective nuclear charge, this is a larger effective nuclear charge. So we expect this one to be small, right? And this is next smallest, and then these are bigger. Okay? So doing isoelectronic ions, the cations are smaller, the anions are bigger. And as you get higher charge, the anions get bigger and bigger and bigger. And as you get higher positive charge, they get more small. Okay? So choose the larger atom or ion from each pair. Do we even need a periodic table to do this one? Potassium or potassium plus 1? Which one's bigger? Potassium. Because K1 has lost an electron. Here, we don't need the periodic table either. Fluorine or fluoride? Fluoride. Because this one has an extra electron. You add stuff on the outside, it gets bigger. Now these two. Here's where a periodic table is helpful. So here's chlorine, and it's going to gain an electron to be like argon. And here is calcium, and that's going to lose 2 electrons. To be like argon. Because really, it's better to think of the periodic table as a cylinder, right? It's just a spiral going around. So potassium really is right next to argon, but it's hard to draw that on here. It's like a flattened world map, right? And you're going from like Hawaii to Russia, right? And you're going, "Argh!" when actually it's not that far at all. So these have the same number of electrons as each other. Which one's going to be bigger? The one that has extra electrons or the one that lost electrons? Extra electrons will be bigger. So this guy. Any questions?
So when you have more positive charges than negative charges, the greater the difference between the positive and negative charge, like the greater the demand for the imbalanced.
Well, these two would have a greater difference in size than, say, K plus and Cl minus. The difference in size would be bigger. Yeah.
So it pulls it in because it's just that much more positive than there's that many more protons than there are electrons. So it pulls them in because it's much
Yeah. Yeah, so this one has more protons, same number of electrons. This one has fewer protons, same number of electrons. So it's got fewer protons, it pulls more weakly, so they can kind of stretch out a little bit. And this is, these kinds of questions are like favorites on test banks in the ACS. Another trend is ionization energy. It's important to understand what we mean by ionization energy. So the ionization energy is kind of long to write out. Oftentimes we'll call it IE, ionization energy. That's the energy needed to remove an electron. Now we talk about the sodium losing an electron to become like neon, and it wants to do that. Well, the electron doesn't just fall off. It's just that you can pull it off really easily. It's not giving it away for free. You have to pay for it. It's just very cheap. As opposed to like bromine or another halogen, you want to take an electron away from them, it's going to cost you a lot. So this will always be positive. You always have to pay the atom to remove an electron. So what this means here is here you have an element M, right? And this is always done in the gas state. We don't need to worry about that. We add the ionization energy, and we pull an electron off, and that gives us a +1 ion. We can do this again. The second ionization energy is the second time you do this. So you take the +1 ion, you put in the second ionization energy, and you pull off another electron, and now you have a +2. And you could go third and fourth and fifth, just pulling off electrons. As you pull them off, they become harder and harder to pull off. So first ionization energy decreases as we go down a period. Down a group. As we go down the periodic table. Well, what's happening to size when we go down in the periodic table? It's getting bigger, right? So it's getting bigger the electrons on the outside are further away from the nucleus, they're easier to pull off. Okay? Helium is very small. The electrons are very close to the nucleus. It's hard to pull them off. As it gets bigger, it's easier to pull them off. So if we looked at first ionization energy going across a period from left to right, the size trend is what? Going from left to right. It gets smaller, right? Because of the effective nuclear charge. It doesn't seem to make sense, but I said it did, so you have to believe me. Right? It gets smaller. Well, is it harder to pick the electrons off? A smaller one or a bigger one? It's harder on the smaller, easier on the bigger. Right? Okay, so that's not really sticking. So the big Fresno Fair, not the Fresno Fair, the big Fresno Fair is going on, right? When I had fewer children, we would occasionally go to the Fresno Fair. But it's a great place to lose a child, right? I only have 2 hands. I had 6 children, right? Big family. Would it be easy for me to lose a child at the fair?
Yes.
Yeah, really easy. In fact, I let my brother and sister-in-law take 2 of my kids once, and they almost lost one. And they had my 2 and their 1. And I was like, yeah, I'm not going. Ton of money and lose a kid. Bad idea. So then you think about this mom who has 1 child, right? Is she going to lose that child? No way. She's holding on to their hand, right? Even the mom with 2 kids, you can get 1 on each hand. You can hold on to 2, but after that, you're just out of hands.
You get those little backpacks.
Yeah, I didn't go that far. Okay. Okay, so I tell you that story to help you remember that it's easier to pull electrons off of a big atom. It's easier to lose children from a big family. It's harder to lose electrons from a small atom. It's harder to lose children from a small family. Okay, so as we go across the periodic table, the atoms get smaller, and it becomes harder and harder to remove their electrons. Okay? These are the actual numbers, which we're showing you here, and then we won't look at them ever again. Another thing that can help you remember is, does fluorine lose electrons ever when it becomes an ion? Have we ever seen it do F+? No. Have we seen lithium lose an electron? Oh yeah, all the time. These guys lose electrons all the time. So it kind of makes sense that their ionization energies should be smaller because they do that. These guys are trying to gain electrons. They're just not going to lose electrons.
So shouldn't hydrogen then be like the hardest to ionize compared to helium? Because it only has 1 electron. Is it that long?
Well, hydrogen just has to break all the rules, pretty much. And, if you're looking at the trend, actually I think helium is smaller than hydrogen. Effective nuclear charge. So it's okay by that. So on the basis of periodic trends, if possible. Tin or iodine. So here's iodine, and there's tin. You kind of have to talk yourself through these problems because it's a 50-50 chance, right? And it's kind of confusing. So it says determine which element in each pair has a higher first ionization energy. So more energy, harder to lose an electron. Am I looking for a big atom or a small atom? Which family is hard to lose children? a small family. So to get the highest ionization energy, I'm looking for the smallest atom. So my trend going across is that they get bigger or smaller? They get smaller. This is the smallest atom of the two, so it has the highest ionization energy. Let's just skip the ones in the middle and do fluorine and sulfur. So here's fluorine, and there's sulfur. We're looking for the smallest, right? So if we go across, fluorine is to the right of sulfur, which would predict that fluorine is smaller. But if we go down, they get bigger, and that predicts that sulfur would be bigger. So these trends are opposing each other. So this would be another place where if they're not forcing you, you guys say, can't tell, because the trends are opposite. If they force you to choose, the up and down trend is stronger, and so the sulfur is bigger, fluorine is smaller, and so the fluoride would be the higher ionization energy. You just really have to talk it through. I mean, that's how I do it. And I teach this stuff. Of course, there have to be exceptions, right? We see exceptions in this trend when we get between groups 2A and 3A. So boron has a smaller ionization energy than beryllium, which is not what we expect. But what's happening is that boron is losing a 2p electron, which is higher in energy and is easier to remove. And beryllium would be losing a 2s. So it says draw the orbital diagrams. So 2s, 2p. This is boron. Let's move over here. 2s, 2p. This is beryllium. How many electrons does boron have? 5. How many valence electrons? 3? Mm-hmm. So 2 of those electrons are core electrons, and 3 of them are valence electrons. So we have 3 valence electrons. So we put those in. 1, 2, 3. Beryllium has 2 valence electrons. 1, 2. This is higher energy than S. Not a lot, but it is. That's why this one fills up faster. This room costs more, and so it's easier to convince this guy to leave, because it's like, well, then I don't have to pay for the room. And so this one's easier to remove than that one, even though boron is smaller than beryllium. I won't try to trick you with that. Another place is between 5 and 6. It's like between nitrogen and oxygen. So here, oxygen is to the right of nitrogen. It's smaller. We would expect it to have a higher ionization energy, but it's actually got a lower ionization energy, because the electron we're removing here has to pair. It has to sleep upside down in the bed, right? And so it's easier to remove this one than one of these guys. Again, I don't expect you to do that on a test. We also see trends in successive ionization energies. So we're looking at first, second, third, fourth, fifth. How are they changing? So here looking at sodium and magnesium. Sodium's first ionization energy is very small. When sodium loses 1 electron, it gets a noble gas configuration, right? So that's the good place. To pull another one off is huge. I don't know quite about the math there, but it's like 9 times bigger, right? It's a huge jump. And then there's this jump. Not quite as big. Well, why is that so much bigger? Hold that thought. Here's magnesium. Right next to each other on the periodic table. So magnesium's first ionization energy. Again, magnesium is a little smaller, so we expect the first ionization energy to be a little bigger, and it is. So there's the first ionization energy. Here's the second ionization energy. This is only about twice as much. And it's the third one that's the huge jump. Because when you're losing one and then you lose the second one, magnesium has a noble gas configuration. That's like, you're going down in energy, and that's like the bottom. And now if you want to pull another one off, you're going back up the hill on the other side. Here, sodium loses one, it gets to the bottom, and going up on the other side, you're going to have to do a lot of pushing. So this is just showing how, this is the jump in ionization energy, because what we're doing here is, for sodium, the first one is a valence electron, and this was originally a core electron. It's closer. And here, magnesium, when you get to the core electrons, that's when the big jump comes.